Hello everybody and welcome to Differential Equations. In today's video, we're going to describe the basics of what a differential equation is. And then we're going to explore a couple of differential equations that arise from real-world scenarios. So to begin with, what is a differential equation? A differential equation is just any equation that contains a derivative. So for some mathematical examples of differential equations, I could give us, for example, y prime plus y equals 0. This is saying I'm thinking about a function y equals some function of x or some function of t, and I want my function to satisfy the condition that when I take its first derivative and add it to itself, the result of that is 0. So that would be an example of a abstract mathematical differential equation. It's just an equation containing a derivative. And as the course goes along, we are going to learn about what it means to solve equations like this, and we're going to learn the different techniques that can be used to get solutions to equations like this. For now, let's just see how differential equations can appear from some very common real-world scenarios. And to begin with, let's talk about the differential equations that arise from the situation of population growth to start with. So in this scenario, we might have some function y of t that represents the population of a certain species at time t. Now, as a rule, if your population is large, then the rate of change of that population will be correspondingly large as well. Because if you have a large population, you have a lot of members of that population to reproduce, have babies, and to make the next generation even larger than before. So I'll say note that unless the population is constrained by some kind of environmental factor, the rate of growth of the population is proportional to the population's current level. Now, I've highlighted rate of growth here because in calculus, we've seen that the rate of growth, the rate of change, is a very important quantity because that is the same thing as the derivative of the population over time. The derivative of the population with respect to time, symbolically here called dy dt, or we could also say y prime. So when we say that the rate of growth of the population is proportional to the population's current level, that translates directly into the mathematical equation that the rate of growth, y prime, is proportional to, so it's equal to a constant multiple of, whatever population you have right now. This statement that we've just given symbolically down here, y prime is equal to some constant k times your current population. This is the mathematical version of what we've said in English up here. The rate of growth of population is proportional to the population's current level. So just by thinking about that real world phenomenon, the more rabbits you have, the more rabbit babies you're going to have as a rule. Just by thinking about that, we have obtained a differential equation, an equation containing a derivative that represents that real world scenario. Let me give you another example of a differential equation that arises just very naturally from thinking about what happens in a real world situation, what happens physically. So let's explore the differential equation corresponding to temperature change, for example. In this scenario, you might have a function capital T of lowercase t, which is tracking the temperature of an object at time lowercase t. Now, how an object's temperature changes over time is going to be affected by the temperature of its environment, right? If you have a hot cup of coffee that is located in a cold refrigerator, that cup of coffee is going to cool down and it is going to lose temperature over time. By contrast, if you have a, frozen chicken that you are leaving out to defrost on the counter, you have a cold chicken in a warm environment, the chicken's temperature will increase over time and it will get warmer. You have a positive rate of change in such a situation. So, what we can say in English to capture that reality is we can say that the rate of change of temperature is proportional to the difference between your object's current temperature and the ambient temperature of your environment. So if I use my mathematical symbolic language to rewrite this statement that we just made in English, I could say that the rate of change of temperature, the derivative of temperature, T prime, is proportional to, it is some number multiplied by the difference between the current temperature of the object and the ambient temperature. So I could say something like T sub A for ambient temperature. And I could then subtract T for the object's current temperature as defined above. So here we can see if the temperature of the object is larger than the temperature of the room, if the object is hotter than the room, then when we subtract, this quantity is going to become negative. So our T prime, our rate of change, our derivative is going to be negative. And so the object will cool down in this case. Whereas if the object is colder than the room, and if the room is hotter than the object, this difference will be positive, so T prime will be positive as well. So here we have our differential equation, which reflects this physical phenomenon of how an object heats and cools in a room. And this equation is called Newton's law of cooling. Let's continue to explore some differential equations that arise very naturally from just applying physical laws to physical situations. And the next one that I want to explore together with you is the differential equation that comes from having an object, a mass, attached to a spring, and then, displacing that object and letting it bounce on the spring and watching how that object moves on the spring over time. So I'm going to define a function y of t, and this is going to track an object's position as measured relative to equilibrium on a spring at time t. Now, when I talk about an object at equilibrium in this context, I'm talking about you take your object, you hang it from the spring. That object's weight is going to pull the spring down to a certain position. And then, if left alone for a minute, the object will just stabilize and hang there at a certain level. And that position right here, where the object naturally hangs on the spring, is what I'm referring to as equilibrium position. If I go in there and I start messing with the object and I push it upward, for example, this would be captured by a positive position, a position that's above equilibrium. And if I, by contrast, take the spring and pull it down and stretch it out such that my object is down here, now my object is below equilibrium, so this would be captured with a negative value of y, or a negative position. When I go into the spring and I disturb the position of the object from equilibrium, I'm going to experience a force. If I push the object above equilibrium, I'm going to experience a force from the spring trying to push the object back down. And if I disturb the object by pulling it below equilibrium, then I'm going to experience a force from the spring trying to pull it back up. That force that we experience from the spring is called the spring's restoring force. The spring's force trying to pull this object back into equilibrium position. So let's try and write down a mathematical expression that would capture the restoring force in a situation like this one. Now, the first thing that I will observe is that if I move the object above equilibrium, the restoring force is going to act to push the object back down. And if I move the object below equilibrium, then the restoring force is going to act to try and move the object back up. So that's my first observation, that the restoring force is always going to act in the opposite direction of the object's current position. If the object is above, the force will act down. If the object is down, the force will act up. So I'll make that note in a bullet point. Direction of force is opposite position. The other thing that I will recall as I just think about, in life when I have messed around with springs, the strength of this restoring force is going to depend on how far that object is away from equilibrium. If I take my spring and I really, really crunch it and I really compress it, and I push that object way, way up there so that my position is far above equilibrium. In this case, the restoring force that I'm going to feel is going to be even stronger than it was before. I push the object far from equilibrium, and the spring will resist strongly in order to try and bring that object back to equilibrium. So I will note that as well. The magnitude of the restoring force is proportional to the position. The further from equilibrium you go, the stronger the restoring force will become. So, putting those two pieces together, if I'm going to express this first force symbolically, I'll call it F1 for the first force, then the first force is proportional to, so it's some number times the object's current position, but there is an opposite happening here in terms of direction. So I will capture that by applying a minus sign in the expression. The spring's restoring force is proportional to the position. It is some number times position, but the direction is opposite, so I will capture that by applying a minus sign in this equation. Now, in a scenario like this one, there is potentially another force acting on this object as it moves, and that is whatever force might be imposed by drag, air resistance, or fluid resistance. If your object is, nice and aerodynamic, maybe the air resistance won't be such a big deal. But if you're dealing, for example, in the physics lab, we have it so that you attach like a cardboard sheet to the spring. In this case, the cardboard sheet is so flat and is encountering so much air as it moves, you really do have to consider air resistance in a case like this. Now, air resistance also has some physical properties that we can use to write down a symbolic formula for the air resistance. And the first property of air resistance, or any kind of drag, is that the direction of the air resistance force is always in the opposite direction of the object's movement slash velocity. If your object is moving forward, then the air resistance is acting backward. If your object is moving up, the air resistance will act down. Air resistance will always act in the opposite direction of the way that you're moving. So the direction of the air resistance force is opposite of the direction of your velocity. Similarly, it's been found that the magnitude, the strength of air resistance is proportional to the object's velocity, at least at relatively low speeds. As you move faster, you experience more air resistance. As you move slower, you experience less air resistance. So from this, let's write down an expression that represents the air resistance in a case like this one. The air resistance force, the second force that you might have to consider, is proportional to the object's speed. So I'll capture that with a number, I'll call it beta, which is traditional in this context. Beta times the velocity, which I will recall is the first derivative of position. Beta times the first derivative of the object's position. And then to capture the fact that the direction of force is opposite the direction of velocity, I'll apply a minus sign in this expression to capture the force and the velocity are happening in opposite directions. So from that, the net force is the sum of these two non-negligible forces acting on this object as it moves. The net force would be the sum of this piece here, negative k times y, the restoring force of the spring, and this air resistance force, negative beta times y prime. Now I'm going to remember from the basics of Newton's laws of motion that net force was equal to mass times acceleration, where acceleration is equal to the second derivative of position. Since position is being called y, I can go into that famous equation and I can replace the acceleration with y double prime. And I've just found that in the case of an object attached to the spring, the net force is equivalent to negative k times y minus beta times y prime. So this differential equation is the one that corresponds to an object that is attached to a spring. If you disturb it from equilibrium and then you watch its position change as it bounces up and down, the position of the object at any time obeys this formula. And we will come back to this equation several times throughout this class as we learn more and more techniques for working with differential equations. Now, the last two examples of real-world differential equations that I want to explore with you are a little bit more advanced and a little bit more complicated. So we won't derive the equations from scratch, but let's have a look at these equations that someone else has created, and let's read them and interpret them and understand the story that each of these differential equations is telling. So, for example, if you have two species that are interacting with each other, maybe like a population of rabbits and a population of wolves that are eating those rabbits, then the so-called Lotka-Volterra equations have been created to capture what is happening in a situation like that one. So let's pop open this link and let's have a look at what we're dealing with. So we have two species here. Species number one is represented by x as a function of time, and species number two is represented by y as a function of time. And so we have two differential equations given here on this page. One, which is the rate of change of the first population over time, dx dt, and the second, which is the rate of change of the other population over time, dy dt. Now dx dt is set equal to alpha times x minus beta times xy. And let's try and make sense of what's going on there. What they're saying is that the rate of change of your population is going to be affected first of all by the current population that you have. The rate of change of the number of rabbits is going to be partially proportional to the number of rabbits that you already have. So this is exactly the same as what we wrote down earlier when we were deriving this differential equation for population change. The rate of change of the population is proportional to what you currently have. That's what's happening right here in this first term. A number times your current population. But then you have this extra term in the back, negative beta times xy. Now this term here, x times y, is capturing the interaction between species X and species Y. The more that you have of species X, the more that you have of species Y, the more interaction you can have between those two species. And so the product here captures that interaction between species X and species Y. Notice that this term appears in the equation with a negative sign, taking away from the rate of change of x. And what this is saying to us, the story that is being told by this equation, is that when species X and species Y interact, that is bad for species X. That has a detrimental and negative effect on species X because that's contributing negatively to the rate of change of this population. Which totally makes sense because in this scenario, X is representing a prey species, and by contrast, Y is representing a predator species. So every time X interacts with Y, some of X is going to get eaten up. So it makes total sense that this will have a negative effect on the population. Now, by contrast, let's look down here at this second differential equation, which is representing the rate of change of y over time. So here is how the predator species is being affected. And what we can see is that the predator species benefits from interaction because this xy term in the second differential equation is showing up with a positive constant. So when the predators and the prey interact and the predator gets to eat the prey, that benefits that population, which is why that interaction term with the xy is positive here. By contrast, the predator species is effective negatively by itself. We see a term in here, negative gamma times y. So the larger your current population of predators, the more negatively that affects the species' future. And this term right here is capturing, for example, things like competition. As you have more predators, they are competing more with each other for territory, for reproductive partners, for food, or the predators suffer for having more of themselves around. So these two differential equations together tell the story of how the predator species and the prey species interact with each other and interact with themselves.